Alright, so we're going to look at geometry. Just going to start with chapter 1. And a lot of chapter 1 deals with terminology, definitions, notation. You've probably seen a lot of it before, but we'll just kind of work through it here. So we're going to start with something called inductive reasoning. And inductive reasoning is based on observed patterns, and that's something that you're used to doing in your normal everyday life. So you see an event happen once or twice, and you generalize that event to make predictions about the future. Your conjecture is the conclusion that you reach using inductive reasoning. So it's an educated guess. So you see something happen, you make a conjecture depending on what you think the pattern will be. So if we look at the next items down here, January, February, March, we recognize those as months. We see that they're in order, so our conjecture would be that the next one would be April, May, June, July. The next are our numbers, and we can see we're just going up by 2, 2, 4, 6, 8, so our next conjecture would be we're counting by 2s, we do 10, 12, 14, so on and so forth. Our next one maybe is a little bit trickier, but not by much. We see that we're again dealing with numbers, and we're going up by perfect squares. 1 is 1 squared, 4 is 2 squared, 3 squared, 4 squared, 5 squared, 6 squared is 36, 7 squared is 49. So again, these should be easy. It's just looking at a pattern. And what we're going to spend a lot of time doing in geometry is taking our conjectures, our inductive reasoning, trying to turn that into the opposite, which is called deductive reasoning. And we're also looking for things called counterexamples. So if we have a counterexample, that's something that shows a conjecture to be false. So let's say that we have something, a statement like a number is always greater than its reciprocal. So if we want to find a counterexample, we want to take a number, which could be anything in this case. There's no specifications on whether it's rational, irrational, or whether it's an integer or a whole number. So we just take anything. Let's take a half. And if we take the reciprocal of that, that's 1 over our number. So 1 over a half becomes 2. Is 1/2 greater than 2? It's not, so that's false, which gives us a counterexample. We also have some basic building blocks, some terminology of our geometric shapes. So a point is a location, so it specifies usually with an ordered pair a location. Space is the set of all points, so that gives us 3 dimensions. We're going to generalize usually to 2 dimensions, but spaces are 3 dimensions as we go through this. A line is a series of points that extends 2 opposite directions without ends. So sometimes people talk about a straight line. Well, a line is by definition straight. It's a bunch of points that are lined up, for lack of a better word, and it continues forever. Collinear points are points that lie in the same line. So we could kind of easily draw 3 points that don't lie in the same line. We're going to have in a little bit of conjecture. If I take 2 points, I'm always going to be able to draw a line through them. But in terms of 3 points, right, they may or they may not be on a line. If they are on a line, then it's going to be what we call collinear, like that. All right, so we have a plane that is a 2D figure. So a flat surface is also kind of our definition of a plane. And points and lines are coplanar if they lie in the same plane. So the thing at the bottom down here, as we look through it, right, this is a plane, this is a line. So a plane is a little bit harder to represent in 2 dimensions, but it's just a flat surface. And we usually draw it as this parallelogram looking shape down here. All right. If we want to name the line, we have certain notation that we look at. So this is line AB. We draw the A and the B with the double arrow over the top. We could also look at it as BC. That is the same line from B to C because it extends forever. That won't be the same with line segments. And then we could also do AC. So there's different ways that we can name that line. It's all the same line, but we call it congruent line. If I look at the plane, I need 3 points for this to be a plane. So A, B, and D. I have A, B, and D. That is the same plane as B, C, D. We're going to assume those are coplanar. And often what we'll do is use a script letter, a capital script letter, to denote that that's a plane. So that would be plane M. That's often how we'll see it, as opposed to just 3 points. All right. This will be a big term for us. A postulate is an accepted statement or fact. It's something that we assume to be true. So when we build our geometric reasoning, we have to start with something. And so we begin with things that we just assume as a fact, and we build from those. Those are called postulates. All right? So our first one, 1, 1, is through any 2 points, there is exactly one line. So this is what I mentioned a little bit before. If I take points A and B, and I draw a line through them, there's not another line that will exist. So we call this line M with a lowercase m. There's not going to be another line that goes through those 2 points, right? And that's something that we just assume to be true. Postulate 1, 2 is if 2 lines intersect, then they intersect in exactly 1 point. So this will be something that we call a conditional down the road. It has an if statement and a then statement. But if we draw 2 lines and they intersect, they can only intersect at 1 point. And this is where I talk about a definition of a straight line, right? I can't have a curve. That's what we call a curve. So lines are by definition straight. If they cross or intersect, they cross at 1 point. Our third postulate, if 2 planes intersect, then they intersect in exactly 1 line. And that's that line right there. Now this is a little bit harder for people to recognize, but we try to draw 2 planes. So if you imagine like a floor and a wall intersecting, that intersection is a line. So that line forms where they intersect. And then our fourth postulate of chapter 1 is through any 3 non-collinear points, there's exactly 1 plane. So if we were to take 3 points from our example up here, like this corner point, another corner point, and this point up here, there would be 1 plane that would capture all 3 of those points. Not necessarily going to be true for 4 points, but for 3 points, there'll be 1 unique plane that goes through those 3 points.